Section 1. Introduction. In my introductory video about Fermat's last theorem, I spoke quite abstractly about arithmetic in rings other than Z, and I gave two examples of such rings, Z adjoin I and Z adjoin omega, where omega is a complex cube root of 1. I told you that in these rings there's a Euclidean algorithm, and there are notions of greatest common divisors, units, and primes that give unique factorization. At the time I mostly wanted to highlight the similarities between these rings and Z, but now let's have a closer look at the details in a special case. Section 2. Arithmetic in Zi. First of all, let's just say a word about addition. We saw that Zi as a subset of the complex plane looked like a 2D lattice. All elements could be uniquely written as a plus bi, where a and b were integers, and we add or subtract two elements just by adding or subtracting their real parts and their imaginary parts, that is, their 1 components and their I components. The set 1i is called an integral basis for Zi, that is, a basis in the sense of linear algebra, but with integer coefficients. In some sense, all the rings of interest to us act like this under addition. They will all just look like copies of Z to the n, in other words, n-dimensional lattices. And while it's not always easy to write down integral bases for them, integral bases do always exist. So there's not much to say about addition. As I said in my last video, what we're interested in is multiplication. Non-zero integers over Z can be written as plus or minus some 2's times some 3's times some 5's, and so on, as long as we only multiply finitely many things together. So what does Zi look like? Here's the lattice picture again. I'm going to define the norm function, n, from Z adjoin I to the natural numbers, including 0, which sends a plus bi to a squared plus b squared. This is just a function sending a complex number to the square of its magnitude. So it's multiplicative in the sense that n of zw is n of z, n of w. In the case of Zi, this norm function n is going to solve all our problems. So for example, I told you that Zi had a Euclidean algorithm, and it is with respect to this norm function. That is, given a and b, elements of Zi, I can divide a by b to get a quotient q and a remainder r in Zi, and that remainder will either be 0, so a equals bq, or it'll be smaller than b with respect to n. In other words, a equals bq plus r, where the norm of r is less than the norm of b. This is what allows the algorithm to terminate. Here's the geometric idea behind why it works. Let's try dividing a, which is 6 plus 4i, by b, which is 1 plus 2i. What that means is, by travelling from the origin along multiples of b, I want to land on or close to a. Okay, b has norm 5, so I want to end up somewhere inside this circle here. Let's try b minus ib plus b minus ib plus b. Now we've landed in the circle. So the quotient q is 1 minus I plus 1 minus I plus 1, which is 3 minus 2i. And the remainder, this distance here, is a minus qb, which is minus 1. That has norm 1, which is less than 5. Exactly as before, this algorithm can be used to calculate greatest common divisors, it will give us Euclid's lemma, and so on. Here's something else we'll want to know. What are the units of this ring? Remember that a unit is some u in Zi with a multiplicative inverse. In other words, such that there exists a v in Zi with u times v equals 1. And we can do this geometrically too. First of all, let's just think about this point up here, u equals 4 plus 5i. Its norm, the square of its distance from 0, is 41. Could this element be a unit? Well, if so, then there must exist some v such that u times v equals 1. So by taking norms, 41 times the norm of v must be 1. So the norm of v must be 1 over 41. So v must lie on this tiny circle of radius 1 over root 41 about the origin. But there are no elements on this circle. If you think about it, this tells you how to find all the units. Since norms are always non-negative integers, if the norm of u times the norm of v is 1, then the norm of u and the norm of v must both be equal to 1. So both u and v lie on the unit circle. So the only possibilities are plus or minus 1 and plus or minus I, which are all units, as you can see from this table. So, what are the prime elements of this ring? Well, here's a simple observation. If the norm of x is a prime integer, then x is a prime element. After all, suppose it's not. Then x can be written as the product of two non-units, say x equals a times b. Then the norm of x is the norm of a times the norm of b, and that's the product of two integers which are both greater than 1. Okay, so we could just play around with some elements and see what we get. So for example, if I take the norm of 1 plus I get 2, so 1 plus I must be a prime element. If I take the norm of 2 minus I get 5, so 2 minus I must be a prime element. In fact, if you think about it, what we're asking is, when is a squared plus b squared prime in Z? And maybe I'll say more on this some other time, but for now, let me just give you the answer, which is the following classical result. A prime number p is a sum of two squares, if and only if it's 2, or it is equal to 1 mod 4. So, if p is 2 or it's 1 mod 4, then there exists some x in Zi such that the norm of x is p. In fact, in this case, p equals x times x bar, and x and x bar are both prime elements. This is the prime factorization of p inside Zi. But, if p is a prime integer that is 3 mod 4, then there doesn't exist an x with the norm of x equal to p. Notice that this gives us a full answer in this case too. If p is 3 mod 4, then the norm of p is p squared. And so if p is, say, a times b, where a and b are two non-units in Zi, then the norm of a and the norm of b must both be equal to p. But we've just shown that this can't happen. So p must still be prime in Zi. Okay, so let's draw a diagram of how primes in Z factorize as primes in Zi. We have 2 factorizing into 1 plus I times 1 minus I. We have the primes that are 1 mod 4, so 5, 13, 17, 29, and so on, factorizing according to however they can be written as sums of two squares. And we have the primes that are 3 mod 4, which don't change when we pass from Z to Zi. One final thing to note about this diagram, there are other prime elements that I haven't written here, such as minus 2 plus 3i, or minus 3 minus 2i, or 2 minus 3i. And the reason I haven't written these is these are all just units times 3 plus 2i, which I've already written. So these primes are called associate to each other. And in this case, we might as well consider them as basically the same prime, at least from the point of view of unique factorization. With that in mind, let me just make the remark that 1 plus I and 1 minus I are associates. So this is really the same prime occurring twice. So I'll just update this diagram to reflect that. And now we can see that there really are 3 distinct types of behavior. In passing from Z to Zi, a prime will either split into 2 primes, it'll remain inert, or it'll ramify, which means that it will be associate to the square of a prime in Zi. Okay, are there any more primes in Zi? Are there any that don't occur by factorizing prime integers? Well, it turns out, and it's not hard to prove, that the answer is no. This is all of them. So we have our units and our primes. As an exercise, you might like to try doing everything I've just done for Z omega, where omega is this complex cube root of unity. The method's very similar. the details are all going to be subtly different. I gave you a hint in my last video that 3 had 2 prime factors and they were both associate to omega minus 1. So, what's the norm function? N of a plus b omega, where a and b are integers. What are the units of z omega? What are the primes of z omega? Section 3. When things go wrong. Unfortunately, most rings are not this nice. Let's see some examples of where problems can arise. Example 1. Units in z adjoin root 2. The rings we've dealt with so far have been imaginary quadratic extensions of z. In other words, the element we were adjoining was not a real number. And we got a nice 2D lattice out of it. We used this when working out the norm. The norm was just the square of the distance from the origin in the complex plane. But z root 2 is a real quadratic extension, so how do we draw it? The right norm function for z root 2 is the norm of a plus b root 2 is a squared minus 2b squared, where a and b are integers. Okay, we have two options. Either we draw it on the real line. We just end up with points scattered everywhere if we try that. Or we can draw it as a lattice, but we have to recognize that this is artificial. This is not a drawing inside the complex plane. Either way, we accept that the picture no longer respects the norm function. N is multiplicative, but this lattice is now a purely additive picture. Notice, in fact, that the norm is already different from how it was before, because it can take negative values. And we can already see that the geometry doesn't match up to our intuition by noticing that the norm of 1 is 1, but also the norm of plus or minus 3 plus or minus 2 root 2 is 1, so the units definitely don't lie on a circle anymore. In fact, 3 plus 2 root 2 is a unit, because 3 plus 2 root 2 times 3 minus 2 root 2 is 1. But that means that its nth power is a unit for all positive integers n. And here's what they look like. As you can see, the numbers in front of the 1 and in front of the root 2 are growing. It looks like we're going to have infinitely many units. So we have a new problem. How do we write them all down? Is this all of them? What do they look like algebraically? Example 2. Euclidean algorithms. So far we've been using the existence of a Euclidean algorithm, the existence of a Euclidean algorithm with respect to a norm function, and being a unique factorization domain, quite imprecisely and quite interchangeably. But they're actually different things. In general, norm Euclidean implies Euclidean, implies unique factorization domain, but not conversely. For example, Harper showed that z adjoin root 14 is Euclidean, but not norm Euclidean. Lenstra showed the same for z adjoin a complex 32nd root of 1. Motzkin showed that z adjoin 1 plus root minus 19 over 2 has no Euclidean algorithm, even though it is a unique factorization domain. By the way, I recommend Motzkin's paper for those who don't have much background in reading mathematical papers, but who want to give it a go. It is a tough read, but it doesn't assume much prior knowledge, which is quite rare. It's also available free online. Example 3. Non-uniqueness of factorization. Here's a quick example inside z adjoin root minus 5. 6 is 2 times 3, which is 1 plus root minus 5 times 1 minus root minus 5. Now, we can calculate the norms of these elements. 2 has norm 4, 3 has norm 9, and 1 plus or minus root minus 5 both have norm 6 in this ring. So it feels like we should be able to factorize these further. Say, 2 is P1, P2, where both P1 and P2 are primes of norm 2. And 3 is P3, P4, where both P3 and P4 have norm 3. And then 1 plus root minus 5 is P1 times P3, and 1 minus root minus 5 is P2 times P4. That would be nice, But unfortunately, these elements, P1 to P4, don't exist. Both of these factorizations, 2 times 3 and 1 plus root minus 5, 1 minus root minus 5, are minimal and they're completely different. So 6 doesn't factorize uniquely into primes in this ring. By the way, it can get even worse than this. There are rings in which you can have factorizations of the same element into different numbers of irreducible elements. Now, in an ideal world, these P1 to P4 would exist, even if as something other than numbers, and we could reclaim our unique factorization that way. But that's a story for next time.